This video is still on groups, and we are still checking if certain sets under certain operations they are groups. So now we have here a set with 4 elements: 1, minus 1, I, minus I. These are the complex numbers, okay, under the usual complex multiplication, and we want to check if this is a group or not. Okay, and in order to check if it is a group, we still have to go for these 3 axioms, right? Have to check associativity, identity, and the existence of inverse for each element. We are going to use this table. This is the so-called Cayley Tables. I'll talk about this on another video, of course, but here I'm going to use this. So we'll put 1 minus 1, I minus I, 1 minus 1, I minus I. So it's pretty obvious that 1 is the identity. So the identity times each element, you will get the same element, right? I minus I, and the identity here. So this is multiplication, right? 1 times 1, 1, 1 times minus 1, I, and minus I. Okay. Okay, so this is not hard. Then 1 times minus 1, minus 1, you just do all the table. If check that you have all elements on each row: 1 minus 1, I minus I, 1 minus 1, I minus I. You have all elements on each row and on each column too. Okay. So you can check that it is the operation is associative. There is an ID. The ID, as you can see, is 1, and each element has 1 inverse. Check, for instance, a funny thing. The element minus 1 times A inverse should equal the identity, right? So the identity is 1, right? So your inverse is going to be minus 1, right? So minus 1 is the inverse of itself, okay? Because minus 1 times minus 1 times minus 1 equals 1, and 1 is the identity, okay? So this set under the complex multiplication, there is an inverse, right? So yes, it is a group. What about the set of the rational, let us say the positive rational numbers under the usual multiplication? Is that a group? Well, you can check. Yes, it is a group. The inverse will be of any element A and the positive rationals will be 1 over A, okay? Because 1 times 1 over A equals 1, and 1 is the identity for the multiplication and the positive rationals. So yes, this is a group. What about the set of positive real numbers? So this will be, if you take the rational numbers, what you have here is the irrational positive numbers. Okay, under the usual multiplication, of course, this union with 1. Well, this is one of those tricky questions, because if you check associativity, you can check that the set and the operation is associative. You can check there is an identity, and you can also check that there will be an inverse. Okay, you check these 3 things, but it's not a group. Why? Because this set is not closed for this operation. If you pick element square root of 2 times square root of 2, you get 2, and 2 is not in this set. So this is one of those the old questions. When you have a set and a given operation, check first if A operation B, you will get C. Check if C is in G. Okay, so check if the set is closed for the operation. Okay, that's the case here. The 3 axioms, they all work, but the set is not closed for the operation. Okay, you can get 2 elements. You get 2 elements, or the same, yes, 2 elements. You operate, perform the operation, and you get an element that is not here, an element that is not in the set. Okay. Now let us check if matrices of dimension 2 by 2 under the usual addition of matrices, if this is a group. So we take an arbitrary matrix A, B, C, D. Okay, this is a 2 by 2 matrix. Okay. So under addition, is this a group? I'm going to call this matrix, okay, A1, B1, C1, D1, and I'm going to get another matrix, A2, B2, C2, D2. I think that this is okay, right? So, and I'm going, you know what addition, what matrix addition is, right? You're going to add A plus B, so it will be A1 plus A2, B1 plus B2, C1 plus C2, and D1 plus D2. Okay? Okay. Okay. Okay, adding 2 matrices, A plus B, so A plus B, you got a matrix that is in the same set. Is that you got a 2 by 2. Okay, now you check for associativity. Okay, you check if it is associative. You check for the identity. Now we are used to the identity of numbers being for addition 0 and for multiplication 1. Here the identity has to be a 2 by 2 matrix, right? So it will be a 2 by 2 matrix, but the identity for addition would be 0 0 0 0. Okay, and we still have to check, so associativity, you can check that. Identity, we have this identity, you can add, if you add A plus the identity, you will get A. Okay, now we have to check the inverse. Well, the inverse is for matrix A, for instance, will be minus A minus B minus C minus D. Okay, so this will be the inverse matrix for A. Okay, so there is a inverse matrix. So 2 by 2 matrices under addition, they are a group. I just want to leave this note here. Okay, I'm not going to explain this. I'll get back to this. The set Zn 0 1 etc. So for instance, Z3 will be 0 1 and 2. Okay, because you stop at n minus 1, so at 2. Of course, for n equal 1 or greater than 1, is a group under addition module n. For any j in Zn, the inverse of j is n minus j. This is very easy to check. You can check all this. This group is usually referred to as the group of integers module n. For instance, here in Z3, you will be, so you would have the set Z3 and you would be adding module 3. Okay, so for instance, 1 plus 1 equals 2, 1 plus 2 equals 3, but you're adding module 3, so this will be 0. Okay, 1 plus 3 equals 4, but you're adding module 3, so this will be 1. Okay, etc. I definitely will get to this, and we are going to talk about this a lot in other videos.